So in our last video, we were showing that this algorithm that we were looking at was correct, and we did part 1 and part 2. So we have 2 parts left, part 3, which was called the eventual falsity of the guard. So what does this mean? You need to show that after a finite number of iterations, G becomes false. Basically, you make sure that the loop eventually stops. Well, I know that after we do m iterations of the loop, my value for I is m. Well, this means that G becomes false after m iterations of the loop. Because remember, our guard G is that I is not equal to m. So after m iterations of the loop, the guard becomes false. So the very final step you have to do to show that this algorithm is correct is correctness of the post condition. So you need to make sure that after the loop is done, you get what you were expecting to get. So I'll say, according to the post condition, the product should be m times x after executing the loop. Well, if G becomes false after n iterations, well, remember what G is. G is I equals m. If we're also assuming that IN is true, then I has to be n, and our product has to be n times x. So now, because both of these things have to be true, since both G is false and IN is true, this means, in particular, if we look here, that m equals I equals n, and in particular our product was n times x, but that's the same thing as m times x. And we got back what we wanted to in the end. Okay, our goal was to get the product to be m times x, and that's exactly what you get when you exit the loop. So again, there are 4 steps in showing that an algorithm is correct, and we've gone over all 4 of those. The 2 previous ones, which were basis property, inductive property, and then 2 in this video, eventual falsity of the guard, correctness of the post condition.